Hi, welcome to Weekly Physics with Sir Danny. Today I'm going to show you how to solve motion problems that involve rectilinear motion or uniformly accelerated motion. When we're talking about rectilinear motion, an object is experiencing a constant rate of change in terms of its velocity. When an object changes its velocity, an object experiences acceleration. But if there's a constant change in the rate of velocity, then there is a constant acceleration experienced by the object. And there are many ways on how to find the acceleration or any physical quantity that involves in motion when we are dealing with rectilinear motion or uniformly accelerated motion. Hi, and these are the different kinematic equations that we use in uniformly accelerated motion or rectilinear motion. The first equation is x is equal to x naught plus v naught times t plus 1/2 at squared, followed by x is equal to x naught plus v sub x times t, which is just the basic velocity equation but derived using the displacement as the unknown. We also have the third equation. The final velocity is equal to the initial velocity or v naught plus the acceleration times its time, which is derived from the acceleration equation. And we also have the average acceleration or average velocity rather, which is equal to the half of the final and the initial velocity. And the last one, we have the square of the final velocity is equal to the square of initial velocity plus 2a times the quantity of the change in displacement x. We have a problem that a certain car who is at rest accelerates at a certain 15 meters per second square in 2 seconds. And in 2 seconds, how far does the car was able to cover in terms of displacement x? Obviously, we cannot use equation 1 because equation 1 doesn't have the value of time and the variable for x and also for acceleration. Equation 2, we cannot use equation 2 in that case because it doesn't have the value of x, or there's no unknown x in the equation. But that leaves us to equations 3 and 4. Equation 4 has x, initial velocity, time, and acceleration. While equation 4 has final velocity, initial velocity, acceleration, and x. Between the two equations, 3 and 4, equation 3 is more suitable in answering the problem because equation 4 doesn't have the value of time, but we have the value of the final velocity, which is also unknown. Since we were able to identify what particular equation that we can use in addressing the problem, the next step is substitute the given variables. So we have here x is equal to the initial displacement, which is equal to 0, plus v naught times t, which is equal to 0, times 2 seconds, plus 1/2 a, which is equal to 15 meters per second square, times t 2 second square. Now we can simplify this one. If we're going to simplify this, we have 0 meter plus 0 meters per second times 2 seconds. That will give us 0 meter. Why? Because the seconds here will cancel. Second divided by second is equal to 1 plus 1/2 15 meters per second. I prefer to square the time first. So 2 square will give us 4. Second square will give us s square. Then 0 plus 0, this is equal to 0. That leaves us 1/2 15 meters per second times 4 second square. We can simplify this. This will become 1/2 we can simplify this one as, let me here, one half 15 times 4, that will give us 60 meters. Why meters? Because the second square will also cancel out. Second square divided by second square, that will give us 1. So 1/2 of 60 will give us x is equal to 30 meters. If we're going to check this one, having our final x here is equal to 30 meters. If we're going to check this one, this is equal to 30 meters also. So our answer is correct.